Okay, today we're going to start graphing rational functions, and we're going to approach it using our transformation rules that we've done in the past. Now, today is just really to wrap your head around what the shape of the graph looks like and how simply it moves back and forth. Starting tomorrow and through the rest of the week, we're not really going to be graphing using transformations. I'm going to teach you some other strategies to graph that are more appropriate for more complicated graphs. Okay? These are just super basic. Let's get a feel for what the graph looks like. Okay? You've seen this graph when we talked about inverse variation, and I said this is the shape of the rational parent function. Okay? Now, you might notice here it says the reciprocal parent function. Okay? Technically, those mean the exact same thing. It's the reciprocal of x, so they call it the reciprocal parent function. I have always known it as the rational parent function or the rational function. So as much as I try to change it to reciprocal, it might not happen. Okay? Let's fill out this table. If I were to plug in negative 10, what am I going to get? Okay? If I were to plug in negative 5. Negative 1/5. What if I plug in negative 1? 1. What if I plug in negative 1/2? Negative 2. Dividing by 1/2 is the same as multiplying by 2. What if I plug in negative 1/8? Negative 8. What if I plug in 0? Undefined. Why? Yeah, you can't have 0 in the denominator. So at x equals 0, this function is undefined. The reason is that we can never divide by x. Okay, what if I plug in 1/8? 1/2? 1, 5, and 10. Okay, now I know it's not going to be perfect when you plot the points, but please go ahead and do the best you can to get these points plotted. And before you connect the dots, I want us to talk about it for a sec. So just get the points plotted for now. Okay, so before you connect these points, we know something important happens at x equals 0. What happens? What happens to the graph? It's undefined, right? At x equals 0, the graph is undefined. What that creates at the line x equals 0 is an asymptote. And what an asymptote is a line that you approach. You get closer and closer and closer to it, but you can never cross it. Okay? An asymptote, hyperbolas have asymptotes in them. An asymptote is part of the parent function of a rational function. It must be drawn in, okay? And it must be labeled. So you're going to represent asymptotes as dotted lines, and you're going to label them with an equation. So our vertical asymptote is the line x equals 0. Will this graph ever be able to cross the y-axis? No, why not? But we haven't decided that this is an asymptote yet. All I'm asking you is, will we ever touch the x-axis? Did I say y? Oh, sorry. You're right. If we can't touch the y-axis because we have this asymptote. Now I'm asking you a separate question. What about the x-axis? Will we ever touch the x-axis? Why not? Good. The x asymptote is the line y equals 0, right? Will 1 divided by a number ever give us 0? No, it'll give us 1/2, 1/3, 1/4, 1/5, 1/6. Will it keep getting smaller and smaller and smaller though? Yeah, but it's never going to cross 0. We're never going to, you can only get 0 by having a 0 in the numerator. And we have 1 in the numerator. We can't get 0 in the numerator. So you have another asymptote at y equals 0. Dotted line, label with the equation. Now you can connect your points. Those asymptotes act as magnets. They pull the graph towards them.
Is this supposed to look like an inverse function?
A what?
Like the inverse functions that we did like last Monday, the variation.
Yes, an inverse variation is modeled by a rational parent function. Okay, what's the y-intercept of this graph? There isn't one. So you can either write none, or you can write DNE for does not exist. You cannot, however, just leave it blank, because in that case, I don't know that you actively knew there wasn't one. It looks like you could have just skipped it. Okay, so don't leave it blank. You need to write a none or does not exist. Okay, is there an x-intercept? No, so we're going to write none. What's the domain of this curve? What happens at 0? It doesn't hit it, so you need to use a parentheses and a union to skip over that 0. These parentheses are really, really important, okay? Should it look like a bracket, you've messed up, because then you're including 0. And the range in this case would be the same.
And if it was a bracket, it'd be the same thing.
Right. Okay, make yourself a note by your asymptotes. These must always be written as equations. You can never just tell me an asymptote is 0 or an asymptote is 4. It's got to be an equation. The same, on the same hand, the direction of the asymptotes is very important. You need to know the difference between horizontal and vertical. If you are someone that struggles with that, you've got to learn it now. Now's the time. You've reached your deadline. It has to happen. Okay? Horizontal, think of the horizon. Out in front of you, it goes left to right. Vertical, think of how tall you can jump. You go up and down when you jump. Okay? All right, so as I said, for our really, really basic functions today, we are going to use transformations. Starting tomorrow, we're going to look at specific rules for how to graph certain things. Okay? So our parent function is y equals 1 over x. So we're going to talk about what an a value can do, what an h value can do, and what a k value can do. So let's start with the a value. What do you think the a value might do?
Vertical stretch.
Yeah, it's going to cause a stretch or a compression. So when the absolute value of a is greater than 1, and all that really means is when a is a value bigger than 1, we're going to have a vertical stretch. But when a is a fraction, when the absolute value of a is between 0 and 1, we're going to have a vertical compression. And why do you think I'm talking to you about absolute values here?
So we don't get confused.
Yeah, because the negatives are going to do something separate, right?
Yeah.
Negatives in our cases have always done what?
Flip.
Flip. So if you look back at your parent function for a sec, look at what and think about what a reflection across the x-axis would do. You flip the right side down and the left side up, right? The reflection. What about a reflection across the y-axis? Would flip over, it'd flip over. They're going to end up looking the same, right? So what we're going to do is we're going to say if a is less than 0, so if a is negative, we're going to go ahead and call it a reflection across the x-axis. But we're recognizing that with these simple graphs, a reflection across the x and a reflection across the y give you the same thing. Okay. The h value is going to do what it's been doing. If you have x minus h, what does that tell us to do?
Move it over to the right.
Write h units. What if we have x plus h? Left h units. So that's still the same. All right, and last, let's talk about k. If we have a plus k at the end of our function, what does that tell us to do?
Move it up.
Up k units. And what if we have minus k? Down k units. Okay? All right, let's try it. All right, so we're going to think of this in terms as transformations from our parent function. What transformations have been applied? Left 3, down 5. Okay? Now, just as our points would move left 3, down 5, so do our asymptotes. Okay? So the horizontal asymptote was at y equals 0, right? So where is it going to be now?
Y equals -5.
Yeah, because the left 3 isn't going to change your horizontal asymptote, but down 5 does. So you're going to draw in. Remember, use a dotted line. And you want to label with your equation. All right, where is your vertical asymptote going to be? Left 3, so it's going to, what's it going to be at? -3. All right, now I want you to picture moving. I want you to think back on this function, and I want you to picture this point 1, 1, and -1, -1. For today's purposes, you're only going to really worry about moving those points because we're just trying to get an idea, okay? So think about where those would move here. 1, 1, we go left 3, down 5. So it puts us at -2, 4. -1, -1, we go left 3, down 5. -4, -6, okay? And then you use your asymptotes as your guides to fill in your function. What's your domain? All right, and what about your range? Okay, now look at your graph that you just drew. Does this graph have an x-intercept?
Yes.
What is an x-intercept?
Yeah.
Yeah, a root, a solution, where you cross the x-axis. Does this curve cross the x-axis?
Yes.
Yeah. Does this graph have a y-intercept?
Yes.
Yeah. What is a y-intercept? Where it crosses the y-axis, okay? If I asked you, hey, go find the y-intercept, what would you do? Good, you plug in 0 for x. If I asked you, go find the y-intercept, what do you do? Wait a sec. Okay, let's start. Rewind. All right. If I asked you to find the x-intercept, what do we do?
Y 0.
Y equals 0. Good. If I asked you to find the x-intercept,
Wait, for what? What?
Plug in 0 for x.
think about it. If you go to the x-intercept, y has to be 0, right?
Plug in 0 for what?
So you plug in 0 for y. For the x-intercept, or for the y-intercept, it's where x is 0. Okay? All right. Look at number 3. All right, what are the transformations?
Flip across the Y.
Reflect across x and up 2. Let's think about our horizontal asymptote. Is the reflection going to have any effect on that asymptote? No. What about the up 2? Yeah. So it's going to go from y equals 0 to y equals 2. Don't forget to label with your equation. All right. What about the vertical asymptote? Yeah, because the reflection doesn't change it, and the up and down, the up 2 doesn't change it. So it's still at x equals 0.
What's the point of it?
You sure? Okay. Okay, take your point 1, 1. Reflect across the x-axis, and then up 2. So where do we end up at? The same place. Okay, how about the point -1, -1? Reflect across the x-axis, up 2. Okay, use your asymptotes as your guide.
Any other just like eyeball it a little bit? Back.
For now, the big picture is that you're getting the pieces of the graph in the right spot. Starting tomorrow, you're going to have very specific points that you're being asked to graph every single time. Okay? All right, what's the domain of this function? Union 0 to. What's the range? Okay. Everyone okay with that? Does this graph have an x-intercept?
Yeah.
Yes. What is an x-intercept? Across the x-axis. Does this graph have a y-intercept?
Oh, wait.
A y-intercept. Does this graph ever cross the y-axis? No. So, in our examples, we've seen no intercepts, both intercepts, or one intercept. It's totally okay. It just depends on how the transformations and where the functions fall. You have a question?
If you reflected it across the. Oh, I never mind.
Sure? Okay. Okay, look at this equation. Y equals 8 over x. What is happening from our parent function to this? Say vertical what? Stretch by 8. Which does mean you'd multiply your y values by 8. We want to kind of get an idea, so we're going to plug in some points. So what's 8 divided by 16? Or sorry, negative 16. Negative 1/2. What's 8 divided by negative 8? Divided by negative 4? Divided by negative 2? Divided by negative 1? Divided by negative 1/2. Dividing by 1/2 is the same as doing what? Multiplying by 2. What happens if we were to plug in 0? Undefined. Can't divide by 0. Okay, what about positive 1/2? 1, 4, and 8, 16. Okay, the only transformation that's happened is a stretch. So have your asymptotes moved? No. So go ahead and draw in your asymptotes. Dotted line labeled with the equation. All right, do your best and let's plot these points. Notice that your scale is going by 2. And do your best to connect your curve. Does this graph have an x-intercept? No. So remember, you're going to write none or it does not exist. Does this graph have an x-intercept? No. What is the domain of this graph? And what's the range of this graph? Same thing. Okay, questions about that?
Yes.
Yeah.
It doesn't even like
Look different?
no, like the domain. There's like it's still there's still a further gap. You know what I'm saying?
Yeah. So your domain is not necessarily paying attention to this part right here. Think about as you keep getting closer and closer to plugging in 0, you can plug in 1/8. You can plug in 100. You can plug in 1 over 1,000. And you can keep getting closer and closer. Does that make sense? Okay. Other questions? Okay. Last one. We are using y equals 8 over x as our guide. So we're not starting back from scratch. We're starting from the graph we just drew. What are the transformations that have happened to this new function? Good. Don't forget the negative first. Reflect across x. Left 5, down 6. So does the reflection change my asymptotes? No, just the left 5. So we have x equals -5 for my vertical asymptote, and y equals -6. For my horizontal asymptote. Okay, look at the graph right before. Would you agree that 4, 2, and -4, 2 are nice, pretty points? Okay, so let's think about what happens to them. 4, 2, reflect across the x-axis, left 5, down 6. 2, 4, 6. So here's my point. -1, 8. All right, what about -4, -2? Reflect across the x-axis, left 5, down 6. -9, -4. Once you have your points, you can use your asymptotes as guides and draw them in. Questions about how I got that? Okay, what's your domain? To -5. Union -5 to infinity. And our range is -infinity. Don't put up your work yet. It's -6. Union -6 to infinity. Okay, listen up real quick. At the bottom of that notes page, look at the bottom of your notes page. It says add 2 problems. Okay, you see that? Your homework goes from 2 to 4 and 5 to 7. Add number 1 to the instructions on 2 to 4, and add number 2 on this sheet to the instructions from 5 to 7. So put 1 in the first part and 2 in the second part. Okay? Let me know if you didn't get that, and I will come and check in with you.